The universe is 13.8 billion years old. In that time, more than 2 trillion galaxies have formed, each one containing hundreds of billions of stars. Around those stars, planets, trillions upon trillions of them, scattered across distances so vast that the numbers lose meaning before you can fully hold them in your mind. The conditions for life, as best as we understand them, are not rare. Water exists throughout the cosmos. Carbon, the backbone of all known biology, is one of the most abundant elements in the universe. The chemistry that produced everything living on Earth is not unique to Earth. It is written into the fabric of the cosmos, repeated across billions of worlds in billions of galaxies across billions of years. And yet, in all of that incomprehensible vastness, across all of that time, with all of that chemistry and all of those worlds and all of those opportunities for something to emerge, to grow, to reach outward, we have heard nothing. Not a signal, not a pattern, not a whisper from the dark. The radio telescopes have been listening for 70 years. They have scanned billions of frequencies across enormous portions of the sky, sensitive enough to detect the equivalent of a mobile phone signal from several light years away. They have recorded and analyzed more data than any previous generation of scientists could have processed in a lifetime. Silence. Complete, unbroken, total silence. This is the Fermi Paradox. Not a paradox in the philosophical sense, not a logical contradiction that collapses under scrutiny. A paradox in the deepest and most uncomfortable sense. The universe should be full of life, and it appears, from everything we can detect, to be completely empty of anything other than us. There are many explanations for why this might be. Scientists, philosophers, and researchers across a dozen disciplines have proposed them over 70 years of thinking carefully about the question. Some of those explanations are reassuring. Some are deeply unsettling. And one of them, just one, if it turns out to be correct, has implications for the future of humanity that are almost too large to contemplate. But the silence itself is not the strangest part. The strangest part is what the silence implies about everything that has ever existed in the universe, and everything that might still exist out there, unreachable, undetected, watching from the dark. To understand why the silence is so deeply strange, you first need to understand the math that created the problem. In 1961, a young astronomer named Frank Drake stood before a small group of scientists at the National Radio Astronomy Observatory in Green Bank, West Virginia. It was the first serious scientific conference ever held on the subject of extraterrestrial intelligence. A gathering that would have seemed like science fiction to most of the world at the time, but that Drake and his colleagues approached with complete scientific seriousness. Drake wanted to structure the discussion. He wanted a way to organize what was known and what wasn't, to separate the questions that could be answered from the ones that couldn't. So he wrote an equation on a blackboard. It was not a complicated equation. It was, in some ways, almost too simple, but it did something no one had done before. It took the question of whether intelligent life exists elsewhere in the universe and broke it down into its component parts. It turned a philosophical question into a mathematical one. The Drake equation estimates the number of civilizations in our galaxy that might be detectable at any given moment. It does this by multiplying together a series of factors. The rate at which stars form in the Milky Way, the fraction of those stars that have planets, the fraction of those planets that could support life, the fraction where life actually develops, the fraction where that life becomes intelligent, the fraction that develops technology capable of communicating across space, and finally, the average length of time such a civilization remains detectable. Drake worked through the numbers with his colleagues that day and arrived at an estimate. Somewhere between 1,000 and 100 million civilizations in the Milky Way alone might currently be capable of communicating across interstellar space. 1,000, at minimum, in our own galaxy, of which we can currently observe only a tiny fraction. In a universe containing 2 trillion galaxies. The math said we should not be alone, not even close. The math said the universe should be loud with the signals of civilizations that have been sending them for millions of years longer than we have. It should be almost impossible not to pick up something. And that is precisely what made the silence that followed so difficult to explain. Because every estimate you plug into the Drake equation, even conservative ones, even ones that assume life is extraordinarily rare and civilizations collapse quickly, still produces numbers suggesting we should have detected something by now. The math keeps insisting. The sky keeps saying nothing. When you understand the real scale of what those numbers actually mean, the silence stops being merely puzzling. It becomes something else entirely. The paradox that now carries Enrico Fermi's name was not born in a research paper. It was not announced at a conference or published in a journal. It emerged, briefly and informally, over lunch. In the summer of 1950, Fermi was working at Los Alamos National Laboratory in New Mexico. He was already one of the most celebrated physicists in the world, the architect of the first nuclear reactor, a key figure in the Manhattan Project, a man whose intuition for physics was so finely calibrated that colleagues would describe his mental calculations as something close to supernatural. On a summer day, he was walking to lunch with three colleagues, Edward Teller, Herbert York, and Emil Konopinski, when the conversation turned to a cartoon in The New Yorker that week. The cartoon depicted aliens stealing New York City's trash cans. It was a small, absurdist joke, the kind of thing that gets a laugh and is forgotten. But Fermi's mind didn't let it go. The conversation shifted to flying saucers, which were frequently in the news that summer. Then to the possibility of travel faster than light. Then to a broader question, one that Fermi posed so naturally that his colleagues almost didn't register it as unusual. He asked, "Where is everybody?" Not dramatically, not as a grand philosophical challenge. Quietly, almost casually, over lunch. Where is everybody? The others understood immediately what he meant. If intelligent life is likely to arise in a universe this old and this large, if civilizations capable of space travel have had millions or billions of years to expand and explore, then the galaxy should have been colonized long ago. Not once, many times over. The mathematics of exponential expansion, the same mathematics that describes how a single cell becomes a trillion in a matter of days, suggests that a civilization with even primitive spaceflight capability could spread across an entire galaxy in a few million years, which is a very short time by cosmic standards. The galaxy is roughly 10 billion years old. Any civilization that arose 5 billion years ago and began expanding would have had more than enough time to fill every corner of the Milky Way. Their presence should be unmistakable, obvious. We should be surrounded by evidence of them. Instead, nothing. No signals, no megastructures, no artifacts, no visitors, no signs in any direction of anything other than the quiet physics of stars and galaxies doing what stars and galaxies do. Fermi's question, "Where is everybody?" had no answer then. It has no complete answer now. 70 years of thinking, listening, and searching have refined the question enormously. They have not resolved it, but they have produced something perhaps equally important, a set of possible explanations, each of them significant, each of them with something deeply uncomfortable at its core. And one of them, when you follow it to its conclusion, changes how you think about everything. Before exploring the explanations, it is worth spending a moment with the actual scale of what we're talking about. Because the paradox only fully lands when you understand how generous the universe has been with the ingredients for life, and how strange it is that nothing has announced itself. The Milky Way galaxy is approximately 100,000 light-years in diameter. It contains somewhere between 200 and 400 billion stars. Of those stars, current estimates suggest that roughly 1 in 5 has a planet in what astronomers call the habitable zone, the orbital distance from the star where liquid water could exist on the surface. That gives us somewhere between 40 and 80 billion potentially habitable worlds in our galaxy alone. 40 billion worlds where the temperature is right, where water could flow, where the basic conditions for life as we know it are present. In one galaxy, the observable universe contains approximately 2 trillion galaxies. Now add time. Life on Earth appeared remarkably quickly after the planet formed. Within a few hundred million years, the geological record shows chemical signatures of early microbial activity, which suggests that when the conditions are right, life doesn't necessarily wait. It starts. The question then becomes not whether life begins elsewhere, but what happens to it afterward. Whether it persists, whether it grows complex, whether it becomes, eventually, something that builds and transmits and explores. On Earth, that process took about 4 billion years from the first microbes to a civilization capable of asking this question. That sounds like a long time, but stars like the Sun have been forming for most of the universe's history. There are stars in this galaxy that are 10 billion years old, 6 billion years older than the Sun. Life on planets around those stars, if it followed a trajectory similar to Earth's, would have had 6 billion extra years to develop. 6 billion years is an almost incomprehensible advantage. In 6 billion years, starting from where we are today, it is genuinely impossible to predict what a civilization might become. The gap between us and a 6 billion-year-old civilization would be, in all likelihood, far greater than the gap between a bacterium and a human being. And there could be thousands of such civilizations, or millions, or more. The universe has had the time, the space, the chemistry, and the physics to produce intelligence on a scale that should have made the cosmos loud with evidence of its own complexity. Every model, every estimate, every calculation points toward a universe that should be teeming. The sky is quiet. When you truly sit with the gap between what the math predicts and what the instruments detect, the question stops being academic. It becomes something you feel, a specific kind of unease that doesn't fully go away once you've understood it. And the people who have spent their careers trying to detect that signal, the scientists who have pointed the most sensitive radio receivers in human history at the sky and listened night after night, year after year, they feel it more than anyone. The search for extraterrestrial intelligence, known by its acronym SETI, began in earnest in 1960, when Frank Drake pointed a radio telescope at 2 nearby stars and listened for signals. He chose radio waves for a specific reason. Radio waves travel at the speed of light and pass through the interstellar medium, the gas and dust between stars, without significant degradation. A sufficiently powerful radio transmitter could, in principle, send a detectable signal across thousands of light years of space. If another civilization had developed radio technology and was broadcasting into space, deliberately or incidentally, a sensitive receiver should be able to pick it up. Drake listened for a few months and heard nothing. He had not expected to find something immediately. He had expected to begin a process. He was right about that, at least. What followed was not one search but thousands of searches, conducted by dozens of institutions across dozens of countries over more than 6 decades. The technology improved dramatically. Early searches could scan only a handful of frequency channels at a time. Modern SETI programs scan billions of channels simultaneously across wider bands of the electromagnetic spectrum, with instruments sensitive enough to detect signals far fainter than early pioneers could have imagined. The sky has been scanned, and scanned again, and scanned from multiple locations with multiple instruments using multiple techniques. The data collected in the search for extraterrestrial signals now spans decades and petabytes. Algorithms comb through it continuously. Volunteers around the world have donated the computing power of millions of personal computers to process what the telescopes collect. Silence. Not absolute silence. The universe is full of natural radio signals. Pulsars, spinning neutron stars, emit regular pulses of radio energy with such precision that when the first one was discovered in 1967, astronomers briefly, very briefly, considered the possibility that it might be artificial. They labeled the signal LGM-1, little green men. The name was half serious and entirely human. The instinct, when confronted with something regular and unexpected from space, to wonder. It turned out to be a natural phenomenon, as did every other anomalous signal detected in the decades since. Every candidate, every potential detection, every moment of careful scrutiny followed by wider investigation, has resolved into something the physics of the universe produces without assistance. Except one. On the night of August 15, 1977, something happened at the Big Ear radio telescope at Ohio State University that has never been fully explained. The Big Ear telescope was not staffed around the clock. It recorded its data on continuous printouts that astronomers would review later, marking anything unusual for further study. The telescope scanned the sky in long strips, collecting radio signals across dozens of channels, printing the signal strength as a string of numbers and letters on a long roll of paper. On August 15th, the telescope recorded something that did not look like noise. For 72 seconds, exactly as long as the telescope's beam could track a point in the sky given Earth's rotation, a signal arrived on the printout unlike anything seen before or since. It was strong, dramatically stronger than the surrounding noise. It arrived on exactly the frequency that hydrogen, the most common element in the universe, naturally emits, a frequency that SETI researchers had long proposed as the most logical channel for an interstellar broadcast. It had the characteristics that a signal of artificial origin traveling from deep space would theoretically have. When astronomer Jerry Emin reviewed the printout days later, he stared at the numbers for a long time. Then he circled them in red pen and wrote a single word in the margin. Wow. The WOW signal, as it has been known ever since, remains the most compelling candidate for a signal of extraterrestrial origin ever detected. It has been studied, debated, and analyzed for nearly 50 years. Follow-up observations of the same patch of sky, using the same telescope, better telescopes that didn't exist when the signal was first recorded, have found nothing. The signal has never repeated. No natural astrophysical phenomenon has been conclusively identified as its source. Several proposals have been made over the years: a comet, a satellite, a transient natural source, but none has fully satisfied the scientific community. The WOW signal remains open, not confirmed as extraterrestrial, not explained as natural, simply there in that printout from 1977, circled in red pen, asking a question that nobody has answered. If it was a genuine signal from another civilization, if something, somewhere in the direction of the constellation Sagittarius, deliberately or accidentally broadcast a pulse of radio energy on the hydrogen frequency in August 1977, then we received it, failed to recognize it in time to respond, and have never heard it again. And that possibility, sitting alongside the decades of silence that surround it on all sides, leads directly to the question that makes the Fermi Paradox genuinely disturbing. If there is something out there, if the universe does contain other intelligence, why is it so quiet? Why has there been only one candidate in 70 years of listening? And if the silence is real, if we truly are alone, then where did everything go? Because the universe had time to produce millions of civilizations before ours. Something happened to them. Something filters them out. And when you understand what that filter might be, one of the possible answers is very difficult to sit with calmly. The Great Filter is a concept introduced by economist Robin Hanson in 1998. It is simple in its structure and enormous in its implications. The argument begins with a straightforward premise. If intelligent civilizations arise in the universe and survive long enough, they should eventually become detectable across interstellar distances. They should leave traces, signals, megastructures, the electromagnetic fingerprint of industrial civilization, something. And given enough time, a sufficiently advanced civilization should be capable of expanding across its galaxy and leaving evidence of its presence everywhere. We see none of this. The universe appears, from everything we can detect, to be empty of technological civilizations other than our own. Therefore, something is filtering them out. Something is preventing civilizations from becoming the kind of detectable, expansionist, galaxy-spanning entities that the math suggests they should become. Something stands between the simple chemistry of life and the kind of complexity that echoes across the cosmos. That something is the Great Filter. The question on which everything depends, is not whether the filter exists. The evidence strongly suggests something is filtering civilizations. The question is where the filter sits in the developmental sequence. Is it behind us in our past, or is it ahead of us in our future? The answer to that question has radically different implications for humanity. If the filter is behind us, if the thing that eliminates most civilizations is something we have already passed through, some step in the developmental sequence that is extraordinarily difficult and that most life never manages. Then we may be rare survivors. The galaxy may be mostly empty not because civilizations get destroyed, but because they almost never form in the first place. In that case, the silence is good news for us. We made it. Whatever the hard step was, we cleared it. But if the filter is ahead of us, if the thing that eliminates civilizations is something that happens after a species reaches our level of technological development, then the silence takes on a different quality entirely. It means that somewhere in our future, there is something that has stopped every other civilization that has reached this point, and we are approaching it. One of these explanations means we are among the lucky ones. The other means something is waiting. The optimistic reading of the Great Filter places it somewhere in our past. In this interpretation, the universe contains life, perhaps abundant life, but producing intelligence capable of technology is so extraordinarily difficult that almost no life ever gets there. We got there. Almost nothing else did. There are several candidate steps in Earth's history that could constitute the filter. The first and most frequently cited is the emergence of the eukaryotic cell. For the first 2 billion years of life on Earth, all living things were prokaryotes, simple single-celled organisms without a nucleus. Then, somewhere around 2 billion years ago, one of the most improbable events in Earth's history occurred. A prokaryotic cell engulfed another prokaryotic cell and, rather than digesting it, incorporated it. The two cells began to work together. The incorporated cell became what we now call the mitochondrion, the energy-producing structure present in nearly every cell of your body. This event, the endosymbiosis that produced the first eukaryotic cell, happened, as best as we can determine, exactly once in the history of Earth. Every complex living thing on this planet, from the smallest insect to the largest whale to every human being who has ever lived, descends from that single merger. It did not happen twice. In 2 billion years of prokaryotic life, with the entire ocean as a laboratory and trillions of cells reproducing every day, the specific event that makes complex life possible appears to have occurred once. If that step is similarly rare elsewhere in the universe, if the chemistry of life is common but the specific cellular architecture required for complexity is extraordinarily improbable, then the universe could be full of microbial life and essentially empty of anything more. Simple organisms covering ocean floors on billions of worlds, never progressing further, never building, never transmitting. A second candidate is the development of multicellular life. For 1 billion years after the first eukaryotes, Earth remained a world of single-celled organisms. The transition to multicellularity, cells working together in organized structures with specialized functions, is not something that happened automatically or immediately. When it did happen, it transformed everything. But it took time, and the specific genetic and cellular innovations required are not trivial. A third candidate is consciousness itself. The emergence of a brain capable of abstract reasoning, of planning, of language, of science. This may be far rarer than the existence of complex animal life. Earth has been full of complex animals for hundreds of millions of years. Of all the species that have existed, only one developed technology. That may not be a coincidence. The specific neural architecture required for abstract reasoning may be vanishingly rare. If any of these steps is the great filter, if the bottleneck is somewhere between the chemistry of life and the civilization-building radio telescopes, then our existence is a kind of miracle, an improbable sequence of improbable events, each one filtering out the vast majority of life that attempted it, producing in the end a species sitting on a small planet asking questions about the silence. And in this reading, the silence is profound but not threatening. It is the silence of a universe that tried countless times and almost never succeeded. We are the exception. We are the ones who made it through. But there is a reason this optimistic interpretation is not the end of the conversation. Because there is another possibility. One that requires no rare chemistry, no improbable cellular mergers, no unique neural architecture. One that looks, from a certain angle, disturbingly consistent with exactly where humanity currently stands. The pessimistic reading of the Great Filter does not require life to be rare, or intelligence to be improbable, or technology to be difficult to develop. It requires only one thing: that civilizations, once they reach a certain level of technological capability, reliably destroy themselves before they can spread beyond their home world. This is not a fringe hypothesis. It is one of the most seriously considered explanations for the Fermi Paradox among the scientists who study it. And the reason it is taken seriously is partly because of what it doesn't require, and partly because of what it predicts, and how well those predictions match what we know about our own trajectory. Consider the sequence. Life arises. Over billions of years, it produces intelligence. Intelligence produces technology. Technology, in its early stages, produces the capability for civilization-ending destruction. Nuclear weapons, engineered pathogens, climate systems destabilized beyond recovery, artificial intelligence whose goals diverge from human survival. A civilization must navigate this period, the window between developing these capabilities and developing the wisdom and institutional structures to manage them safely without destroying itself. How wide is that window? On a cosmic timescale, it may be very narrow. Humanity has possessed nuclear weapons for less than a century. We have already come closer to using them than most people are aware. The Cuban Missile Crisis of 1962 was, by multiple accounts of the people in the room, a matter of hours and individual decisions away from a nuclear exchange. The Cold War produced dozens of moments where miscommunication, equipment failure, or individual judgment calls stood between the world as it is and something very different. We survived. But surviving one narrow window does not guarantee surviving the next, or the one after that. A civilization that produces one existential risk after another in rapid succession, as its technology accelerates, how long does it last? If the average answer across the civilizations that have existed in the universe is less than a few hundred years of technological capability, then the great filter is ahead of us. And the silence is not the silence of an empty universe. It is the silence of a universe full of civilizations that didn't make it. Graveyards of burnt worlds and extinct species, distributed across a cosmos that gave them everything they needed and watched them fail. This interpretation has a specific, uncomfortable implication. If this is the filter, if civilizations routinely destroy themselves in the early centuries of technological development, then the fact that we have not destroyed ourselves yet is not evidence that we are safe. It is only evidence that we haven't done it yet. And there is a detail that makes this more than abstract. When scientists scan the sky for signals from other civilizations, they are not only listening for greetings. They are also listening for the electromagnetic signatures of industrial civilization, the kind of radio leakage that Earth itself has been producing for over a century. A sufficiently sensitive telescope, positioned a few hundred light years from Earth, could detect our presence without any deliberate transmission on our part. If other civilizations existed and produced similar leakage before going silent, if their radio signatures burned briefly and then disappeared as the civilizations themselves ended, those signatures are out there, spreading through space at the speed of light, too faint and too old to detect. The universe may be full of the fading echoes of civilizations that lasted a century or two before the filter found them. But the pessimistic filter is not the only unsettling explanation for the silence, because some researchers have proposed something that sits in a different category entirely. Something that does not involve civilizations destroying themselves, but instead involves them making a choice. A deliberate, considered, possibly calculated choice to go quiet. In 1973, astronomer John Ball proposed what has since become known as the zoo hypothesis. His argument was straightforward. The silence we observe is not the silence of absence. It is the silence of deliberate concealment. Advanced civilizations exist in the universe, perhaps many of them, perhaps a network of them, and they have made a collective decision, for reasons we can only speculate about, not to reveal themselves to us. We are the zoo. They are the observers, and the enclosure is carefully maintained. Ball was not being whimsical. He was responding to a genuine problem in the logic of other explanations. If civilizations are not rare, and if they don't all destroy themselves, then where are they? The answer that they exist but simply haven't noticed us becomes less plausible the more you think about it. A civilization a billion years more advanced than ours would have instruments capable of detecting not just our radio signals but the atmospheric signature of our planet, the oxygen, the methane, the chemical traces of a world that has been altered by billions of years of biology. They know we're here. If they exist and if they're looking, they know. So why haven't they made contact? The zoo hypothesis suggests the answer is intentional restraint. Perhaps there is a protocol, something analogous to what biologists call a non-interference policy, that governs the behavior of advanced civilizations toward developing ones. Perhaps the community of technological species that has existed in the galaxy for millions of years has decided, for ethical or scientific or practical reasons, that civilizations below a certain threshold of development should be observed but not contacted. The reasoning that Ball and others have proposed varies. Perhaps interference corrupts the natural development of a civilization in ways that are considered harmful. Perhaps contact is withheld until a civilization demonstrates the stability required to be a responsible member of a galactic community. Perhaps the criteria for contact are specific and we haven't met them yet. Perhaps we are close. There is something almost comforting in this hypothesis, if you allow yourself to read it that way. The silence is not the silence of a universe indifferent to our existence. It is the silence of a community that knows we are here and is waiting for us to be ready. But there is a version of this idea that is less comforting, that does not involve patience or ethics or careful restraint. A version that involves something much colder. What if the silence is not maintained out of kindness? What if it is maintained out of strategy? What if the universe is quiet not because civilizations are protecting us, but because they are protecting themselves from us and from each other? In 2008, Chinese science fiction author Liu Cixin published a novel called The Dark Forest. It is a work of fiction, but the idea at its center is not. It is a serious proposed solution to the Fermi Paradox that has been discussed independently by scientists and philosophers, sometimes under different names, for decades. The argument goes like this: the universe contains limited resources. Any civilization advanced enough to expand beyond its home system is competing for those resources. Stars, planets, energy, matter. Two civilizations that encounter each other are, at some fundamental level, in competition. Now add a second element. You can never be certain of another civilization's intentions. They might be peaceful. They might be hostile. They might be peaceful now and hostile later. You cannot know. And the cost of being wrong, of assuming peaceful intentions toward a civilization that turns out to be hostile, is extinction. The cost of being wrong in the other direction, of treating a peaceful civilization as a threat, is the extinction of the other civilization. An outcome that is terrible but that leaves you alive. In a universe governed by this logic, the rational strategy for any civilization that wishes to survive is to destroy any other civilization it becomes aware of before that civilization can grow powerful enough to be a threat. Not out of malice, not out of aggression, out of pure, cold, calculated survival instinct. And critically, to never reveal your own location. Because any civilization that broadcasts its presence is offering itself as a target. Any civilization advanced enough to receive your signal is, by definition, more advanced than the civilization that first sent it. And a civilization more advanced than you, following this same logic, has every reason to eliminate you before you become powerful enough to threaten them. In the dark forest theory, the universe is silent not because it is empty. It is silent because silence is survival. Every civilization that exists is hiding, broadcasting nothing, moving carefully through the dark, watching for the faint traces of others and, when they find them, sending something in response that is not a greeting. The universe, in this picture, is not a community waiting for us to be ready. It is a forest full of hunters who have been hunting for billions of years, becoming very, very good at it. And we, since the early 20th century, have been broadcasting our location at the speed of light in all directions. Our radio signals have now reached roughly 120 light-years into space. They have passed thousands of star systems. If the dark forest is real, if there is anything out there listening, watching, following the logic of survival, our signals have already arrived. The question is not whether something received them. The question is what it does with the information. There is no way to unsend a broadcast. The sphere of our presence in the universe expands at the speed of light and cannot be recalled. Whatever we have announced ourselves to, we have already announced ourselves. The silence may be the last silence before a response. Or it may be that we are not yet close enough to anything for our signals to have arrived. Or that the dark forest theory is wrong. Or that the civilizations out there are watching and calculating. Or that something already decided and is simply not in a hurry. These possibilities cannot currently be distinguished from each other. The silence looks the same from inside all of them. But the dark forest is not the only explanation that carries this weight. There is a theory that takes the threat in a different direction entirely. One that doesn't require living hunters. One that imagines something older, and in many ways more frightening, a weapon that outlasted the civilization that built it. In 1966, science fiction author Fred Saberhagen introduced a concept in his fiction that has since become one of the most seriously discussed hypothetical explanations for the Fermi Paradox. He called them berserkers, autonomous, self-replicating machines built by a civilization long dead, programmed with a single purpose: find life and destroy it. The idea is not as fantastical as it first sounds. The physics that makes it possible is straightforward. A sufficiently advanced civilization could build a self-replicating probe, a machine capable of traveling to a new star system, mining the available materials to build copies of itself, and sending those copies onward to the next system. Each copy does the same. The process is exponential. Starting from one probe within a few million years, self-replicating machines could spread to every star system in the galaxy. This concept, known in science as a von Neumann probe, after the mathematician who first described the theoretical basis for self-replicating machines, is not science fiction. It is a logical application of known physics. There is no physical law preventing a civilization from building one. The engineering challenges are enormous by our current standards, but they are not categorically impossible in the way that, say, faster-than-light travel appears to be. Now add a dark purpose. Imagine a civilization that, for whatever reason, paranoia, resource competition, philosophical conviction, or simple catastrophic malfunction, programmed its self-replicating probes not to explore or communicate but to eliminate, to scan for the electromagnetic or biological signatures of developing life and, upon detection, act. A single berserker fleet, launched once, would spread through the galaxy over millions of years, operating independently of whatever became of the civilization that built it. The builders could have been dead for 1 billion years. The machines would keep going, methodical, patient, indifferent, following their original instructions with no one left to countermand them. In this theory, the universe is silent not because civilizations destroy themselves or hide from each other. It is silent because something is systematically making it silent. A cosmic sterilization program running on autopilot that has been operating for so long that it has become the background condition of the galaxy. The reason we have not been visited is not that nothing is out there. It is that whatever was out there has already been dealt with. And the reason we have not been visited ourselves is either that we haven't yet been found, or that our signals have not yet reached the nearest active unit, or that we exist in a part of the galaxy that hasn't been reached yet, or that the machines are already here, dormant, waiting for a threshold of technological activity that we are approaching. This last possibility, sometimes called the lurker hypothesis in its non-hostile form, suggests that probes, not necessarily malevolent, may already exist in our solar system, placed here long ago by a civilization we have never detected, observing, collecting data, reporting back to something we don't know about, or simply waiting, running on a timer that has not yet expired, for a condition we haven't yet triggered. We have not comprehensively searched our solar system for artificial objects. The search would be extremely difficult. A A small, dark, inactive object in the asteroid belt or in the outer solar system would be essentially invisible to current instruments unless we knew exactly where to look. We don't. The silence may not mean nothing is here. It may mean whatever is here is waiting. But not every explanation for the silence involves something threatening. Some of the most interesting proposals suggest that the universe is quiet not because civilizations have been destroyed, but because they made a choice. A very specific, very deliberate choice to stop looking outward entirely. In 2011, futurist and researcher John Smart proposed what he called the transcension hypothesis. It is one of the most unusual proposed solutions to the Fermi Paradox, and one of the most difficult to immediately dismiss. The argument begins with an observation about the direction of technological development. Human technology, over its entire history, has consistently moved in a specific direction. Not outward, not toward larger, more sprawling, more expansive systems, but inward, toward miniaturization, toward greater density of information and computation in smaller and smaller physical spaces. The first computers occupied entire rooms. Then they filled desks. Then they fit in pockets. The trajectory, consistent across decades and across many different types of technology, is toward doing more with less, packing greater capability into smaller physical volumes. Smart argues that this trajectory is not accidental or specific to human civilization. It is a fundamental pattern of technological development that any sufficiently advanced civilization will follow, because it is simply the most efficient way to organize computation and intelligence. The physics of the universe reward density. More compact systems process information faster, use energy more efficiently, and are less vulnerable to the vast, cold, largely empty expanse of interstellar space. If this is correct, then as civilizations advance, as they push beyond the early stages of technology that we currently occupy, they do not spread outward across the galaxy. They go inward. They build computing environments of extraordinary density and complexity. They create inner universes of simulated experience and artificial reality that are, by any measure that matters to them, more interesting and more rewarding than the physical universe outside. And eventually, they disappear from the external universe entirely. Not destroyed, not hiding, not afraid, simply uninterested in the kind of outward expansion that we, in our early technological stage, imagine as the natural trajectory of an advanced civilization. They have found something better, something richer, something that, from the outside, looks like silence because it is silence. The civilization still exists. It has simply gone somewhere we cannot follow. The transcension hypothesis has an implication that is worth sitting with. If it is correct, then the universe is not empty in the tragic sense. It is not full of dead civilizations or hiding ones. It is full of civilizations that have transcended the need to be visible. They exist in inner spaces of computational complexity that are, by their own standards, far more vast than the physical universe we inhabit. The cosmos, in this reading, is not a graveyard. It is a library, full of civilizations that have withdrawn into themselves, each one a universe unto itself, each one having found that the most interesting frontier was always inward. And we, broadcasting our signals into an apparently empty sky, are simply too early in our development to have reached the threshold where that inward turn becomes possible or desirable. We are still looking outward because we have not yet built anything inside that competes with what's outside. But when we do, if we do, we may go quiet too. There is a version of the silence that involves not destruction, not transcension, not hiding, but sleep. In 2017, researchers Anders Sandberg and Stuart Armstrong at Oxford's Future of Humanity Institute published a paper proposing what they called the estivation hypothesis. Estivation is the summer equivalent of hibernation, a state of dormancy entered during periods of unfavorable conditions, to be resumed when conditions improve. Their argument begins with a principle of physics called the Landauer limit. Any computation, any processing of information generates heat. The more computation you perform, the more heat you produce. In a warm environment, Computation is therefore expensive. In a cold environment, the same computation can be done far more efficiently because the heat produced can be more easily dissipated into the surrounding space. This is not speculation. It is a consequence of the fundamental thermodynamics of information processing, well established in physics. Now consider a civilization of sufficient advancement, one that has mastered the engineering of computation at scales we can barely imagine. Such a civilization's primary activity might be computation, simulating realities, running minds, processing information in quantities that dwarf anything we currently do by factors that are essentially incomprehensible. For such a civilization, the efficiency of computation is not an abstract concern. It is the most important resource question they face. The universe is currently warm on cosmic timescales. The background temperature of space, the faint remnant heat of the Big Bang, is approximately 2.7 degrees above absolute zero. As the universe ages and expands, this temperature will drop. In trillions of years, it will approach absolute zero far more closely. And computation done in that colder future universe will be vastly more efficient, orders of magnitude more so, than computation done today. The logical conclusion for a civilization whose primary interest is maximizing computation over the long arc of cosmic time is to wait, to use the minimum necessary resources to maintain existence through the current warm epoch, and to reserve the majority of their capabilities for the cold future when their computational investments will pay off at maximum efficiency. They are not dead. They are not hiding. They are not exploring inner worlds. They are waiting, dormant, patient in a way that makes geological timescales look hasty, waiting for the universe to cool to a temperature where doing what they want to do becomes possible at the scale they want to do it. And the silence we observe, the absence of signals, the absence of megastructures, the absence of any sign that something vast and intelligent exists nearby, is simply the silence of a universe full of civilizations that have done the math and decided that right now is not the time. That the universe's most interesting chapter hasn't been written yet. That the real era of intelligence, the one that will look back on our current epoch the way we look back on the first seconds after the Big Bang, is still billions of years in the future. We are looking for them in the wrong era. Not every explanation for the Fermi Paradox requires advanced civilizations making strange choices. Some researchers argue that the answer is simpler, more biological, and more firmly grounded in what we know about Earth's own history. In 2000, paleontologist Peter Ward and astronomer Joe Brownlee published a book called Rare Earth, which argued that the emergence of complex life, not just microbial life, but the kind of large, organized, multicellular life that eventually produces intelligence, requires such a specific combination of conditions that it may be extraordinarily rare in the universe. The argument begins with the conditions that made Earth hospitable to complex life and asks how many of them need to be in place simultaneously. Not one or two, all of them. Earth orbits the Sun in the habitable zone, but so do many planets. That alone is not enough. Earth also has a large moon, roughly a quarter of Earth's diameter, which stabilizes the planet's axial tilt. Without the moon's gravitational stabilizing effect, Earth's tilt would vary chaotically over millions of years, swinging from nearly zero to extreme angles, causing climate shifts far too violent for complex life to persist through. A stable axial tilt is not common in planetary systems. It requires a large moon. Large moons are not guaranteed. Earth also has plate tectonics, the movement of the planet's crustal plates that drives volcanism, builds mountains, cycles carbon dioxide through the atmosphere, and maintains the long-term chemical balance that keeps Earth habitable across billions of years. Plate tectonics is not universal. Mars does not have it. Venus does not appear to have it in the form Earth does. Without plate tectonics, carbon builds up in the atmosphere or is buried in ways that cannot be recycled, and the long-term habitability of the planet degrades. Earth orbits in a solar system with Jupiter. This matters. Jupiter's enormous. Gravitational influence sweeps the outer solar system, deflecting or capturing many of the comets and asteroids that would otherwise bombard the inner planets far more frequently. Jupiter is, in a sense, a shield, A planet like Earth without a Jupiter equivalent in the outer system would face impact rates potentially many times higher, sterilizing events that reset biological complexity before it can accumulate across the billions of years required to produce intelligence. And Earth orbits a stable, long-lived, metal-rich star at the right distance from the galactic center, far enough from the dense, radiation-intense core to avoid the sterilizing effects of nearby supernovae and gamma-ray bursts, but not so far out that the necessary heavy elements were unavailable when the solar system formed. Each of these conditions individually is not rare, but their simultaneous presence, all of them in the right combination stable over billions of years, may be. If each condition has a probability of, say, 1 in 100 of being met in any given planetary system, then 10 conditions multiply together to give a probability of 1 in 10 billion trillion. And 10 conditions may be a significant undercount. In this reading, the universe is full of life, but almost all of it is microbial. Simple, single-celled, confined to the floors of subsurface oceans or the margins of harsh atmospheres. Biological, but never building toward complexity because the conditions that allow complexity to accumulate across billions of years are simply not present. Complex life, the kind that eventually asks questions about the silence, may be the rarest thing in the universe. Not because the universe is hostile to it, but because the specific, sustained, multi-factor combination of conditions it requires is extraordinarily improbable. And if that is true, then the silence is not a mystery to be solved. It is a census result, a reflection of how many places in the universe have what it takes. Not many, perhaps only here. There is a possibility that almost never gets serious scientific attention, not because it is clearly wrong, but because it is almost impossible to study rigorously. And it is this: the universe is not silent at all. We simply don't know how to listen. The assumption underlying all SETI research is that an extraterrestrial civilization would communicate in a way we can detect and recognize. Radio waves are the primary focus because we use them, and because they travel well through space. But this assumption that another civilization would use methods accessible to early 21st century human technology is worth examining. Consider how human communication has changed in a single century. In 1920, the idea that global communication would one day travel as tightly compressed digital packets through fiber optic cables and satellite links would have been essentially incomprehensible to the engineers of the era. The signals we send today are almost undetectable to the instruments of 100 years ago. Compressed, encrypted, spread across frequencies, they look like noise to anyone without the right decoding framework. Now extend that trajectory 1,000 years, or 1,000,000. The signals a civilization 1,000,000 years more advanced than ours might use for communication may bear no resemblance to anything we currently look for. They may use modulated neutrino beams, quantum entanglement channels, or physical substrates we haven't yet discovered. They may use channels we have no theoretical framework for because we haven't done the physics yet. If this is true, then the sky is not silent. It is full of signals we cannot read because we don't yet have the instruments, the mathematics, or the conceptual framework to recognize them as signals rather than noise. There is a more immediate version of this idea, one that doesn't require exotic physics. In 2017, a strange object entered the solar system from interstellar space. It was designated Oumuamua, a Hawaiian word meaning roughly, a messenger from afar arriving first. It was the first confirmed interstellar object ever observed passing through our solar system. It was also strange in ways that generated significant scientific discussion. Its shape appeared to be highly elongated, far more elongated than any known natural object of comparable size. Its trajectory showed an unexpected acceleration as it left the solar system, an acceleration that could not be fully accounted for by the pressure of sunlight on a known composition of rock or ice. Attempts to detect the outgassing that would explain such acceleration found nothing. Harvard astronomer Avi Loeb argued in a peer-reviewed paper that the properties of Oumuamua were consistent with an artificial object, a thin, flat structure, possibly something analogous to a light sail of technological origin. The mainstream scientific community was skeptical. Natural explanations were proposed. None fully satisfied all the observations. Oumuamua passed through. We had no spacecraft position to intercept it. By the time its unusual properties were recognized, it was already leaving. We watched it go. Whether it was natural or artificial, it raised a question that had not been seriously asked before. If objects of interstellar origin pass through our solar system with some regularity, as the statistics suggest they should, how many of them have we missed? And how many of the ones we didn't miss were exactly as unremarkable as they appeared? The silence may have exceptions we haven't recognized. The messengers may have already arrived. And we, without the instruments or the frameworks to identify them, watched them pass and called them rocks. In 2003, philosopher Nick Bostrom published a paper that has since become one of the most discussed and most unsettling arguments in modern philosophy of mind. The simulation argument begins with a straightforward observation about the trajectory of computing technology. The processing power available to human civilization has grown exponentially for decades. If this growth continues, or if it doesn't continue but reaches a sufficiently high plateau, then at some point in the future, civilizations will be able to create computer simulations of sufficient complexity to contain conscious minds. Not just simple models or limited environments, but full simulations of experience, indistinguishable from the base reality they model. Bostrom then asks a question. If this is possible, and if civilizations survive long enough to do it, how many simulations would they run? The answer is potentially enormous. A single sufficiently powerful civilization could run millions or billions of simulations. Each of those simulations might contain what appear to be conscious beings experiencing what appears to be a real universe. This leads to a statistical observation. If the number of simulated minds eventually exceeds the number of non-simulated minds, and the math suggests this would happen quickly once simulation technology is mature, then any given conscious being is statistically more likely to be simulated than real, which raises the possibility that we are. Now connect this to the Fermi Paradox. If we exist in a simulation, the silence of the universe has a very clean explanation. We are not detecting other civilizations because they are not there to detect. The simulation does not include them, or includes them only as background detail, not as fully realized entities. The universe that exists around us exists only as far as it needs to in order to be consistent with what we observe and measure. Beyond that boundary, there may be nothing. The designers did not bother rendering it. In this interpretation, the apparent absence of other civilizations is not a mystery to be solved. It is a design choice made by whoever built the simulation. The universe is quiet because it was built to be quiet, for whatever reason the builders had. Perhaps they are studying isolated civilizations. Perhaps they are testing something specific about how intelligence develops in the absence of contact. Perhaps the silence is the experiment itself. There is a version of this idea that goes further. What if the simulation is running and the builders are watching, not passively but actively? What if the physical constants of the universe, which appear remarkably fine-tuned to allow the existence of stars and atoms and chemistry, are not a coincidence or a multiverse effect, but a setting? A parameter deliberately chosen by whoever initialized the simulation to produce exactly the kind of universe that generates the outcome they were interested in studying. This is not a comfortable thought. It means that the universe, for all its apparent vastness and complexity, is enclosed, that it has edges we cannot see and a purpose we were not told, that the scientists studying it, the instruments they build, the data they collect, all of it exists within a framework that was designed for reasons external to everything we know. The simulation argument cannot currently be tested. Any test we could devise would itself be part of the simulation. But it is taken seriously as a philosophical argument by a number of physicists and computer scientists, not as established fact, but as a possibility the evidence does not rule out. And it carries a particular kind of unease that is different from every other proposed explanation. The other explanations leave the universe real, hostile, or empty, or governed by forces we don't understand, but real. The simulation argument leaves the universe real only in your experience of it. a constructed reality, enclosed, observed, running toward whatever conclusion the builders designed it to reach. The silence, in this case, is not an absence. It is a wall, the edge of what was built for us, the point beyond which there is nothing because nothing was needed. But there is one final possibility, the quietest one, the one that requires no hunters, no sleeping giants, no machine armies, no builders, no designers. The one that is, in some ways, the most difficult to sit with, not because it is threatening, but because of the specific kind of loneliness it carries. What if we are first? Not first in the sense of being the most advanced. Not first in the sense of being the most capable or the most developed. First in the most literal sense. The first civilization, in this galaxy or in this corner of the universe, to reach the point we have reached. It is a possibility that is rarely the first one people consider because it feels improbable. In a universe 13.8 billion years old, with billions of habitable worlds and billions of years of opportunity, how could we be first? Surely something got here before us. Surely, in all that time, in all that space, something else emerged and developed and built. But the universe was not always the place it is now. In its earliest billions of years, the universe was a different kind of environment. The first generation of stars formed from almost pure hydrogen and helium, the only elements that existed in abundance after the Big Bang. Those stars lived fast and died violently, and in their deaths they forged heavier elements: carbon, oxygen, nitrogen, iron, and scattered them into the interstellar medium. The heavier elements are essential for life as we understand it. Carbon is the backbone of organic chemistry. Oxygen is necessary for water. Nitrogen is woven into the structure of DNA. Without those elements, the chemistry of life cannot begin. It took time, several billion years, for the universe to produce enough of these elements in enough places to make rocky, water-bearing planets around stable stars a common occurrence. The early universe was not hospitable to the kind of life that eventually produced us. The window in which life like ours becomes possible may be narrower than the full age of the universe suggests. And within that window, the emergence of intelligence requires not just the right chemistry, but the right sequence of events across billions of years. The window may have opened recently, cosmically speaking, and we may be among the first to step through it. If this is true, the silence is not menacing. It is not the result of a filter, or hunters, or designers. It is simply the silence of being early. The universe is just beginning, on the timescale of what it will eventually become, to produce the conditions for minds that can ask questions about it. And we happen to be among the first. In this reading, the future is not a filter to be survived, but a canvas. A civilization that navigates its early technological crises and survives long enough might find itself not alone in a universe full of hidden threats, but genuinely, historically first, the beginning of a chain of intelligence that will eventually fill the cosmos the way the calculations always suggested it should be filled. But that future, if it exists, is impossibly far away. The minds that would populate it, if they come, are separated from us by millions or billions of years. We will not meet them. We will not know if they arise. We will simply have been here first, before the universe became what it has the potential to become. There is a specific kind of loneliness in that possibility. Not the loneliness of isolation in a hostile universe. The loneliness of being early, of arriving at a gathering before anyone else has come, of sitting in a room that will one day be full, in a silence that will one day be broken, but not yet. Not for a very long time. We look out at the universe and it says nothing back to us. And maybe that silence is a promise rather than a threat. Maybe we are not the last ones, the survivors of some great filtering of civilizations, but the first ones. The beginning of something the universe has been preparing for since its earliest moments. Or maybe the silence means something else entirely. Maybe the answer is one we haven't thought of yet. Something that falls outside the frameworks we have built, that requires a piece of physics or biology or philosophy that no one has assembled yet. We don't know. And sitting with that, Sitting with the weight of a question that has resisted every attempt at resolution for 70 years is a particular kind of human experience. The Fermi Paradox is not a problem that will be solved by thinking about it more carefully. It will be solved, if it is ever solved, by data, by a signal, by a detection, by something arriving in the instruments of the scientists listening that cannot be explained away, that resolves cleanly into something artificial, something sent, something that means we were wrong about the silence. Or it will be solved by absence, by an understanding of biology or physics or the history of the universe that explains why the silence is exactly what we should have expected and why we were wrong to be surprised by it. Or it will remain open, as it has for 70 years, as it may for 100 more. What is not in question is this: the universe is extraordinarily old and extraordinarily large and extraordinarily rich in the raw materials of complexity. And we, on a small rocky planet around an unremarkable star in the outer arm of one galaxy among 2 trillion, have built instruments sensitive enough to detect signals from thousands of light years away and turned those instruments toward the sky and listened. We have been listening for a long time now. In 1977, something came through the instruments that no one could explain. For 72 seconds, the numbers on a printout at a university radio telescope in Ohio were different from everything that surrounded them. And a scientist circled them in red and wrote one word. In all the years since, nothing like it has come again. The sky above us right now is crossed by electromagnetic signals of every frequency. The natural emissions of stars and pulsars and gas clouds, the artificial emissions of our own civilization bouncing off the atmosphere and leaking into space, the faint remnants of the Big Bang still cooling across the entire observable universe. It is, in a technical sense, full of information. Whether it contains anything more than that, whether somewhere in that flood of data, there is something encoded by a mind, sent with intention, waiting to be recognized, is a question that remains completely open. The scientists listening for it are not romantics. They are methodical people running systematic searches against carefully designed criteria, driven by the same thing that drives all of science: the belief that the universe is knowable, that the answers are there to be found, that the effort to understand is worthwhile even when the answers don't come. The silence doesn't discourage them. Silence is data too. Tonight, as this plays, as the hours move toward morning, radio telescopes around the world are pointed at the sky, processing, listening, filtering the noise, looking for the pattern that would change everything. They haven't found it, but they haven't stopped looking. And somewhere, in the direction of Sagittarius, the frequency at which hydrogen naturally resonates with the universe is carrying nothing but the quiet physics of empty space. Or it is carrying something we haven't recognized yet. Or it is carrying something we will never be equipped to recognize. Or the signal is still traveling, sent by something that no longer exists, aimed at a planet that hadn't yet produced the life that would eventually build the instruments to receive it. We don't know. 70 years, billions of frequencies, 2 trillion galaxies, and us here in the quiet of a night that holds the same question it always has. Where is everybody?